So the reminder is that that the way that I grade the way I evaluate your work in this class is by combining two things. One is the observations that I make during class. Those are what's most important. And so the more you can bring to my attention your commitment to learning about physics, the higher your scores are likely to be. I combine my observations with evidence that you turn in when I collect an assignment. And it gives me a lot of flexibility because, for example, if somebody, like yesterday, there was no assignment, but let's say there was. And what I asked you to do yesterday was to figure out some way of determining the connection between the force that this spring exerts and the distance that it's squished. And I'll go through that today. It's pretty easy mathematical connection, and I'll show you. But I also threw out a little bit of a curveball. And what I said was, it turns out that force, the force from the spring, will be the same as the force registered by a force sensor if you have your cart on a horizontal surface and you push the force sensor up against something while you're pushing the spring back. It turns out, whatever the force sensor tells me right now has to be equal and opposite to the force with which the spring is pushing on my finger. And that intuitively is kind of obvious, but it's not actually, like, if you wanted to prove it, it's not. It's kind of like saying, well, if you have a quadrilateral and 3 of the angles are 90 degrees, what's the 4th angle? We all know it's going to be a rectangle with 4 90-degree angles, but prove it. Like, how do you know that it has to be 90 degrees? Like, that's a little bit more complicated. And so is this. You have to draw a bunch of free body diagrams and do a bunch of Newton's third line. So it's possible that somebody yesterday might have thought, hey, wait a second, before I figure out this whole force from the spring thing, I want to figure out why the force the spring is pushing on my finger with is the same as the force being recorded by the force sensor. And nobody did this, which is fine, but had you done it, maybe you would have come up to me and been like, Grigar, let's figure this out. And then we would have talked, potentially for the whole class period, maybe 40 minutes of you and me just talking and drawing pictures and you asking questions and me asking questions of you. We end up with like this great conversation and you've done nothing on the assignment. And what I want you to understand is that that's full credit. You still need to turn something in. You still need to provide some sort of evidence of what went on, because otherwise I'm going to forget because I don't remember anything. But if, for example, you were to write a little note on a piece of paper, draw a free body diagram, take a picture and turn it in, when I go to Canvas and I see, oh yeah, I was talking to this person about the free body diagrams, I remember, full credit. Or even a little comment. Briga, remember we were talking about the free body diagram thing, I never figured out the force from the spring, but ... full credit. Because that's a reminder of what you did. And in that case, if anybody ever came to me and said, wait a second, why'd you give this student full credit? They didn't turn much in. Then I can say, oh yeah, but here's what we did. I can justify giving pretty much any score that I give, any high score that I give, if I can remember what happened. Where things go awry is when people hear that and think, oh sweet, then I don't have to do anything. It's kind of like, you know how some people want to be video game reviewers for a living? Do you know anybody who's been like, I want to review video games? And so, because that was the equivalent of what now people want to be YouTubers or whatever. And so, but 10 or 15 years ago, everybody was going to be a video game reviewer. Why? Because you get paid for playing video games. But what they were imagining, of course, is that they were just going to sit around playing their favorite video games all day long and the money was just going to come rolling in. So you're actually a video game reviewer. You have to play games that you don't like. And then you have to write reviews that other people are going to read. And you get paid if you write good, like it's not as easy as it sounds. It's the same thing in here. The points don't come from you just showing up. They come from you actually trying to learn physics. And I'm willing to give you credit, even if you don't understand something, as long as you are conclusively demonstrating to me that you're trying to understand it. But there's not much I can do if you're not even trying, or if I don't see you trying. So that's where what concerns me most is the people who, like, if I'm up here talking and you've got your screen in front of your face, I don't know what you're looking at. But I'm not dumb, and so I know that it's like not necessarily physics. Maybe it is. It'd be great if it was. And some of you probably are looking at physics, but some of you aren't. And so if you want to convince me that you're actually trying to learn, you have to do something, right? Like, I'm not, the default isn't that you have convinced me. The default is just nothing. Like, the default is neutral. If you want me to think that you're actually trying to learn, then you have to, like, prove it to me. You have to do more than just, like, kind of quietly show up and like have your laptop open in the back. And when it comes to the activities that we do, it's the same thing. I know if you're thinking, if you bring it to me, I know that you're trying to figure stuff out. If you come up to me and you're like, Brigar, okay, I got this bar, and I figured out these graphs, and the area under this graph is something, but I don't understand why the area under this graph tells us anything about work. That is communicating to me that you're thinking about physics, and that's what I want. But if I never talk to you, you're just back there, I don't know what you're doing. And then when you turn in work, even if it's perfect, which it might be, I still don't know really how much of it was you and how much of it was somebody that you were working with or something online or whatever. So just be aware. And the reason that this is all coming up right now is because I'm caught up on grading. And so when I look at your grades, I think some of you are probably not thrilled. Some of you are fine. If you have an 88% and you want an A, and you missed the last day before spring break, and that like dropped you from a 91 to an 88, you're fine. Like, do the work, I'll help you, but that's not cause for concern. But if you have a C or a D or an F, then just remember what happened first semester, which was, at this point in the semester, I said, if you don't have the grade you want right now, that should be concerning. And some of you didn't do anything different. And you're like 11th and 12th graders for the most part, which means that in a couple years, I fully expect almost all of you, if not all of you, are gonna be in college. And you gotta know that you have to do something, right? College isn't as hard as it was 40 years ago, by any measure, but it's harder than high school. And one thing that I can add to that, like, conversation is perspective, because I teach a college class in the summer. So I teach one of the 200 level biology classes at OSU. It's filled with 18 to, like, mostly 18 to 25-year-old students, just like you're gonna be in a few years. And there's a handful of older students as well. And I know how they do. I see their work habits. I see what happens when they come in and they think that everything's gonna get taken care of for them, because it's just not, it's not. Those of you who need me to do more hand-holding in this class, to kind of pull you up from an F or a D, I'm not doing it. And the reason I'm not doing it is because you've got to figure it out. You could do it. You don't need me to do it. You can do it yourself, but you have to make some decisions to get there. So those of you who are in that position, looking at your grade and not happy about it, just make sure that you are hearing this loud and clear. You've got to do something. At this point, I may or may not accept late work, right? I've told you that before. Like, I'm not as interested in the idea of, okay, I know I have a 13%, but here's 4 months worth of work, take it and grade it. Are you done yet? I'm not doing that. Especially second semester, right? We're gonna hit June, and if you're bringing me work that is more than a few days old, I'm not gonna laugh because I'm gonna be crying, but I won't grade it either, right? I'm not gonna grade it, I'm just not. And if you bring me work now that's more than, like, I mean, if you're gone before the break, I'll help you out, but if you wanna turn in something that we did in February or early March, I don't think so probably, right? Like at this point, we're done with that. You can still pass the class, even if you're not doing as well as you'd like. But be aware that I'm putting this stuff on you because that's where it should be. It's you. You're the ones who should be benefiting from this. You're the ones who should be working. You're the ones who should be learning. My job is to facilitate, present opportunities to give you stuff to think about. And if you do that, well, I'll give you a good grade because that's, I think, a reasonable bargain. Yeah?
What if you turned in something in that time frame you were talking about, but you got like a 2 on it?
Yeah.
Could you like
Yeah.
rework what you were doing?
You should always come and talk to me. And what I would advise you to think about is, how have you been approaching the class? Because if you've been approaching the class like, I care about this, I want to learn this stuff, I want to figure it out, will you please help me? And then you get like a 0 or a 1 or a 2 on an assignment, I'm there, like I will help you. I definitely am not trying to just be arbitrary and say, oh, that was on March 17th, I'm only accepting work for March 18th or later. I'm not gonna do that. But also be aware that I see you and I see what you do, and so if you're somebody who's come in and not worked that hard, then probably not. So yeah, the impulsive collisions lab is the big one. Most people didn't get full credit on that. It's just 1 point. Most of you got between a 2 and a 3. And if you got a 2, if I were you, if that's your only like grade that's below 100%, forget it. It's 1 point. It's not worth even worrying about. If you want to worry about it though, I mean, I'll tell you all right now, there's a video where I presented to you exactly how to collect data, and then I had a data table that I posted to the module in Canvas. And what I said is, I'm gonna ask you for the like very, very few times I ask you to do stuff out of class, but in the video I said, this is something you can do outside of class. And what I wanted you to do was make a graph and use the graph to investigate that relationship between the impulse acting on one cart and the change in momentum of the other cart. I walk you through the whole process in the video. There is data you can use in the module, and if you need help, I'll help you. So it's not supposed to be a punitive thing, but that's what I want. If you want full credit on that assignment, that's what I'm looking for. And I get why a bunch of you didn't do that. You didn't do that because what you're used to is me saying, just do some work and then turn it in and we'll be good. But that isn't what I said that day. That day I said, there's a piece to this where I want you to do some stuff outside of class. We didn't have time to get all the way through it. But also, like, it's just 1 point, maybe 2 points. Like, if you're sitting at an 88% right now, and you are committed to working and learning, you can get the A. You don't have to worry about making up assignments or turning in missing work. I'm more worried about students who have a 60% or a 40%. You're in trouble. And your grade is not likely to change a bunch unless you start changing what you're doing. And there's not many of you, but there's enough of you that I'm taking everybody's time to talk about it. Okay, so that's that. If you have any specific questions like about your individual work, come and talk to me. I want to help you. I want you to all learn. I want you to all get A's. That's what I want. And but I'm going to ask you to do this one certain thing that I know is tricky for some people. So if you still have phones or other devices out, get those put away unless you're looking at physics. And if you're not looking at physics, how the heck am I supposed to know? And what we're going to talk about is energy and work. And this, for the record, I find to be the most fun stuff that we're going to do in physics. Well, actually, oscillations are pretty cool too. But this and oscillations, which are our next 2 units, are just super interesting to think about. There's so much. And so what it starts with is an understanding of the physics definition of work and the physics definition of energy. And those two things, you're gonna have to do a reset. You're gonna have to basically forget what you already think you know about those two ideas. If you have learned the physics concepts of work and energy, probably it's not quite what we need, which means you're gonna have to forget it. And if you've never learned it, then what that means is whatever you think about when you say work or energy is not really what we're talking about here. It's the same word, but a totally different idea. And then the specific task that we're gonna try to tackle is to try to figure out if you have a spring like this one, how much energy is in it, or the way we're gonna think about that is how much work could this spring do? Yeah.
It's gonna build on the data we collected yesterday?
It is, but indirectly, and then we're gonna come back to that data. So ultimately, our first big task is gonna be to make a prediction about how fast one of these supercarts can go if you squish the spring down all the way and then launch it. Okay, and so in order to do that, we have to think about work and energy, we have to think about springs, and we're gonna start by thinking about it more theoretically. So what I hope that you all discovered last class, and I think many of you were at least getting close to this, is that to put it most simply, there's a linear relationship between the squish of a spring and the amount of force it produces. If you made a graph, what you probably saw was something where if you graphed like the distance that you squished it and the force that the spring was exerting, if you did that on the x-axis, if you did the distance on the x-axis and the force that the spring was exerting on the y-axis, most of you probably ended up with data that sort of looked like this, right? If you did a really careful job and you had a really good cart and everything went well, this is sort of what you would have seen. And that looks like a linear relationship. And that, for most springs, is how it works. Most springs will show a linear connection between the amount of stretched or squished, either way, and the amount of force that they produce. The springs that we have on the supercarts, we can't pull them out. They like are blocked. But most springs that are free can be stretched or squished. And it turns out that if we squish them by a certain amount, like a centimeter, it will exert the same force as if we stretch them. So we have two ways we can go. If we think about this distance that we're moving the spring itself, we can move it so the spring gets shorter, or we can move it so that the spring gets longer. And if we think about the force that the spring exerts, it's always going to be in the opposite direction. So if I push this way, let's call this positive. If I push with a positive distance here, then the spring is pushing on my fingers with a force in the negative direction, which means that even though this is most likely the way you graphed your data, if we were to take direction into consideration, the real relationship looks more like this. If your distance goes in the positive direction, the force from the spring will be in the negative direction. And you couldn't have done this with the supercarts, but with real springs, if you stretch the spring in the way I'm holding it, maybe this is the negative direction. If I move the spring in the negative direction, now the pulling force from the spring is this way. So this is what that linear relationship would be like, and I know that wasn't linear, but just pretend that I know how to draw a straight line. And so what this graph is showing is this equation right here, that the force of the spring is going to be related to the distance that it's stretched or squished. And here's where things are going to start to get a little weird, because the variable that we use for that is x. What we're thinking about is the displacement of the part of the spring that's moving. So right now, we would call this position 0. If I move the spring this way, I'm moving into positive positions, and I'm experiencing negative forces. If I move the spring this way, that part of the spring is moving into negative positions and is experiencing positive forces, which means the variable that we use for the stretch or the squish of the spring is x. So x is what we call the spring deflection, which is the stretch or squish. And the force that the spring exerts is related to that by a proportionality constant. It's linear. It's a linear relationship. So this is going to be negative kx, where k is this slope. And k is actually has a name in this particular equation. It's called the spring constant. Or k. And this, if you think about the units of this slope, it's going to be change in force divided by change in displacement. It's going to be newtons, which is our unit of force, divided by some distance measurement, which typically in real data is going to be newtons per meter. So typically this is going to be newtons per meter, and it tells you how much force you'll get per meter of squish or stretch. And a meter is a huge amount of distance for most springs, so sometimes we use newtons per centimeter instead. That's probably what you were looking at yesterday. You were probably measuring centimeters, and then if you were able to tease out a relationship like this, you would have seen, oh hey, there's a constant of proportionality here, and the units of that constant would have been, for your work yesterday, probably newtons per centimeter. And so this ends up being a really useful tool for investigating work and energy, because we're going to have these predictable forces, and they're not constant, but they're predictable and they're based on the distance. If you were to look at the force that a spring exerts as a function of time, it looks more like this, right? It starts off low and then it gets higher and then it goes low again. Or maybe like in the case of these where it's compressed all the way at first, it's gonna look something like this. Right? Starts off large, drops relatively quickly. As time goes by, it's nonlinear, but as soon as we start thinking about that force as a function of distance, it becomes linear. That's pretty easy to work with for a whole bunch of reasons. Right? So this is what I was hoping you were going to see yesterday. Today, we're going to work with a simulation, because the simulation is going to allow you to have a known spring constant and have very precise measurements of deflection. And that means that the data that you get is going to be perfect because it's not real. When you start using the supercarts, you're going to find there's a whole bunch of things that affect the real world performance of the spring. One is that it's not perfect, which means it's not going to be the connection here isn't going to be perfectly linear. The relationship between deflection and force isn't going to be perfectly linear. The other thing is, these springs have a variable K. It's not really variable, but it's a variable effective K. If you turn the plunger, some of you can probably see there's a little nut in there that moves back and forth, and depending on where that nut is, the spring is sort of pre-tension. So sometimes it's easier to squish it down than others. Hi. Thank you. And so what'll happen is any two different supercarts, not only are two different supercarts going to have different Ks, but the same supercart, if somebody happens to turn the plunger, is going to have a different K. So that can be a little bit challenging, but with the simulation, we don't have to worry about any of that. We're just going to work with truly known variables because it's all just built into a model. Okay, so we're going to come back to this when it comes to supercarts on Thursday. We're going to be working with this today in a purely theoretical simulation. So now let's loop back around to what I started talking about, which is these ideas of energy and work. And so when we talk about energy, most people think about things like, well, energy is like pizzazz, or maybe just gasoline, or electricity, or, I mean, there's a million things that people use to describe energy, but it turns out that outside of physics, most of the time when people talk about energy, they're talking about things that have energy, not talking about energy itself. Gasoline isn't energy. Gasoline is just a liquid. It happens to be a liquid that has a lot of energy stored in it in the form of chemical bonds. But so does this, like, plastic, what's the thing, gyroscope holder. This has energy in chemical bonds as well. Not as much as gasoline has. You wouldn't fill up your car with these things, but there's energy stored in these chemical bonds. And so really, when we are talking about energy in physics, all we're talking about is some property of an object or a particle that allows it to speed something else up. That's it. Energy is something that can make things go faster. So this spring, when I squish it, has energy. Because if I squish it, it can make this supercart go faster. The gasoline in the tanks of the cars in the parking lot, the energy in those will make your car go faster. How does that happen? Well, it's complicated, but basically the energy in the chemical bonds gets released, and that causes air to expand, that causes pistons to move, and that causes the axle to turn, and that makes your car go. The energy that we get from our electrical outlets is used to make things go faster too. At every level, electrical energy involves moving particles, electrons. When I plug in this toaster, when I plug it in, nothing happens until I push this lever down. As soon as I push the lever down, then electrical energy pushes electrons around. The little wires in here start glowing red because they're getting hot. They're getting hot because something is moving faster. The electrons in those wires are moving, and they're creating heat because they're moving. There's friction in the wire. So that's what energy is, except we don't actually know what it is. This isn't really a definition of energy. This is a definition of what energy does. The reality is, we don't really know what energy is. We don't really, we can quantify it. We've got all sorts of equations. We can figure just about anything out when it comes to energy. You give a physicist a particle and tell that physicist its speed and temperature, and she can tell you how much energy it has. But nobody can really explain what that is. It can make things go faster. That's really all we know about energy. But that's a pretty straightforward definition. Anything that can make anything go faster is energy. If I hold this pen up above the table and let go, it goes faster. That must have been energy. Energy made this pen go faster. Energy makes things go faster. If I, throw a ball, what made the ball go faster? Energy. Where did that energy come from? Well, it was like my arm. That was the energy. If we use a solar panel to charge an iPhone, and we put the iPhone on vibrate, and somebody calls, and it goes bzzz, that's motion. The iPhone is moving faster than it was before. Where did that energy come from? Well, it came from sunlight. Sunlight has energy, and then that energy was transformed into chemical energy at some point by the solar charger that charged the battery in your iPhone. That energy ultimately made the phone itself move faster. That's what energy does. Work is related to energy, and we'll see how down the road. I know, it's a good one,
I
huh?
hope that's a video.
No, it's not. I know. This is, I don't remember what this is from. I think this might just be a random video. But every time I see it, I think of that episode of The Office where they're playing golf, and Andy gets in the golf cart, and then he crashes into the sand trap, and he just goes flying out of the golf cart in the background. It's really one of the best. It's a great episode. Anyway, so usually when people talk about work, We talk about things like, well, exertion or effort. We almost always think about work in terms of people, but that's not really what work is about in physics. The work that we do can often be related to physics work, but it's not really the same thing. In physics, work is a process, and it's a process that tends to speed things up. We're gonna come back to this later. For now, what we're gonna say is work speeds things up. That's not entirely true. In fact, it's not necessarily true at all. But in the short term, that's how we're gonna think about it. Work speeds things up. Over time, we're gonna shift to thinking about work. This is much more precise. Work is really a transfer of energy. If it speeds something up, then the energy is transferred into kinetic energy, the energy of motion. But that doesn't always happen. So if I can do work, for example, to the lever on this toaster, and once it's all the way down, it's no longer moving. So what happened? Well, the energy is still there. It's stored in the toaster. It's stored in the spring, in the lever. So in that case, the work that I did didn't really speed anything up, or it sped something up for a little bit, but then it still got transferred, right? Like the work that I'm doing to this lever right now didn't just disappear. It's there. I transferred energy into the spring. Now what can the spring do? The spring can make something move. So ultimately, like we think about work as being something that either does or could speed something up. But for the short term, we're gonna think about it like this. Work speeds things up. If you do work, it speeds things up. In order to speed things up, we have to jump through some hoops. Luckily, we've talked about all these hoops. It's not that complicated. First of all, speeding up is one of our types of acceleration. So if work is being done, we'll know because we'll see something accelerate. If I push on this wall and it doesn't speed up, I'm not doing any work. If I push on this supercart and it does, I did work. I sped up that supercart. It had no velocity, and then it had some velocity. Sped up. We know what causes acceleration. It's overall forces, which means in order for work to happen, there must be forces involved. Yesterday, we talked about the idea that objects that don't move can't be accelerating, right? Instantaneously, something isn't moving, it might be accelerating because it might start moving, as soon as that moment, that infinitely small moment in time is over. But if it never moves, it can't be accelerating, which means that for something to accelerate, there has to be a force on the object, and the object has to move. We have to have a force, and we have to have motion. So force and distance, that's what we were looking at with the spring. We were looking at the spring and thinking about, well, as we push it, it's moving. There's forces, there's distance. We're gonna connect the work that we were doing with the springs yesterday to the idea of work in physics. And it's really straightforward. The way we're gonna look at it, it's incredibly straightforward. It actually can get more complicated, and I'll explain a little bit of that, but mostly you won't really need to think about at least some of this stuff. So mathematically, work is equal to force times displacement. So if you have an object that moves, some displacement, this would be measured in meters, and there is a force being applied to that object as it moves, that force would be measured in newtons, then you're gonna have work. Work is gonna be measured in units that are newtons times meters, Newton meters. That, by the way, is the same unit as torque. Totally different meaning here, though. With torque, the force is at a right angle to the distance that we're talking about. With work, the force and the distance the object moves has to be in the same direction. So we'll come back to that in just a second. A Newton meter is also a kilogram meter squared per second squared, because a Newton is a kilogram meter per second squared. So this is like the full unit of work. But all of that is awfully long, so typically we just call it a joule, and we use the abbreviation J. So J is the variable for impulse, but it is the abbreviation for the unit of work. And in order for work to be done, the force applied to the object and the movement of the object have to be in the same direction. If I push on this supercart with a spring in the direction that it's moving, then the spring does work and the supercart speeds up. But if I push on the supercart with the spring not in the direction that it's moving, if it's not moving at all, there's no work being done. If it does move, but I'm not pushing in the same direction as its motion, there's no work being done. The spring doesn't unspring at all. There's no distance associated with the force of the spring. So in general, we're going to be able to deal with this by just always making sure that our forces are in the same direction as the motion of the object. It gets more complicated than that, especially in AP physics. You might need to do some trigonometry, because if you have a force acting at an angle to the motion of an object, like if I push on this supercart down and to your right, then part of my force is in the direction of the object's motion. So I'd have to do some trig to find out the component of the force that's in the same direction as the motion. And there's a couple of side effects of this multiplication operation that you don't need to know the mathematical cause for, but you do need to understand the side effects. The first part is what I just talked about, which is that only the part of the force that is in the same direction as the motion will contribute to this number. So you could push with 1,000,000 newtons and an object could move 1,000,000 meters, but if those two quantities are at right angles to each other, no work is done. If I push down on something with 1,000,000 newtons and it moves horizontally 1,000,000 meters, I didn't do any work to the object. The other thing that's going on here is that this is, in math, we call this a cross product. And cross products are what happen when you multiply vector quantities. Force has a direction, so does displacement. When you multiply something with a direction by something else with a direction, you get something that has no direction. Work has no direction. Work is the process of speeding something up, but it doesn't tell us the direction. I will do the exact same amount of work if I speed up a car from 0 meters per second to 1 meter per second in this direction, or this direction, or this direction, or this direction. There's no direction associated with work. There's no direction associated with energy either, but we'll come back to that on Thursday. Okay, so what does this number tell us? This tells us how much work is done. This is going to be related to the increase in speed, at least as we're thinking about it right now. If work speeds something up, then the amount of work done is going to relate to the increase in speed. But it isn't the increase in speed, because a joule, or a kilogram meter squared per second squared, or a Newton meter is not a unit of speed. This doesn't tell us how fast it's going or how much its speed changes. It just tells us something about how much its speed could change. And more precisely, what work really does is it tells us how much energy is transferred. The way we're thinking about it now, that energy is transferred into motion, speeding something up. There's other places that work can transfer energy. And the last thing that I want to talk about before you start doing your work is that if we're dealing with constant forces, if I push on something with a force of 5 newtons, and I push it for 10 meters, then I can figure out how much work I did. 5 times 10 is 50. 50 joules, 50 newton meters, 50 kilogram meters squared per second squared. How much did I speed it up? Well, I don't know, but it's somehow related to that 50 joules, right? Like, if I do 100 joules of work to that same object, I will sped it up more. So there's some connection between this number and how much of an increase in speed we get. And if we have a constant force over some measurable distance, that's pretty easy to think about. Where things get tricky is when you have forces that aren't constant. So like a spring. Springs exert forces, but they're not always the same. The more you push it, the more force you get. The more you stretch it, the more force you get. So what I want you all to think about today is how much work could a spring do? If I take this spring right here and I squish it a centimeter, it can do some work. It could do some number of joules of work. If I squish it more, it could do more work. If I squish it less, it could do less work. How can we figure that out? How can we figure out how much work the spring can do? In other words, how much energy could it transfer? If you want to figure that out, you're going to have to measure something about force and something about distance. The more distance there is, the more work is done. The more force there is, the more work is done. So somehow, to do these two things, you somehow have to think about the work that's done by the spring is going to be related to forces and the motion of the spring as it moves. But it's complicated because the force isn't constant. So how do we figure that out? And what we're going to do, so you can do this with the supercards too, but I think it'll be a lot easier to figure all this stuff out if you use the simulation called Hooke's Law. There's a link in today's module, and there's a link in this presentation. And what I suspect is that most of you will need most of the period to get this figured out. I'll give you hints as we go. If you happen to get it nailed right away, then you have a second thing to think about. This is going to be our focus for Thursday, but if you have time to think about it today, you can. How would this relate to how much the spring could speed something up? So if we used this spring to push an object, how much, if it does 5 joules of work, how much could it speed up that cart? Or, as we're going to be doing later this week, if I store some energy in the spring of the cart itself, and then I use that spring, oops, I missed. I use that spring to accelerate the cart. How fast can that cart go? How fast will it go as a result of that spring pushing it? So there's some connection between the work the spring does and how much the cart speeds up. That's part 2 of what we're going to be looking at. But your big goal today is this. How can we easily quantify the amount of work a spring can do? How do we figure that out? If we squish a spring a certain amount, how much work will it be able to do? So take 5 first. I mean, you don't have to, but if you want to, take 5. And then when you come back, start looking at that simulation, playing around with it. I'll give you a hint in 10 minutes or so. 15.
Sure, take 5.